Who's first up today, Hanfeng, who's going to talk about local entropy theory for induced actions on probability measured spaces.
Thank you. I would like to thank the organizers very much for the invitation. It's great to be back here. I will talk about the local entropy theory for induced actions on probability measured spaces. I have to apologize that there will be no operator algebras in the talk, though it will involve a little bit function analysis. This is a joint work with New. Let me start with the basic setting. We're going to look at actions of countable discrete groups. So I will put gamma to be a countably infinite discrete group. X will be the action will be on compact measurable space. And we'll look at the induced actions on probability measured spaces of X. So the space of all probability measures. Then given the action of gamma on X, this is a continuous action. It induces one action on the probability measured space because simply probability measured space is determined by X itself. So we're going to look at the relation between dynamic properties of these two actions. Okay. Yeah. In the talk, I will just look at the fixed action and the fixed induced action there. Since we're going to talk about local entropy theory, so let me recall the definition of entropy first. We're going to look at just the classical setting, that is when the group is amenable. So for amenable gamma, that means we take, there is a Fourier sequence, so a sequence Fn of non-empty finite subsets of gamma, so that they become more and more left invariant. Wherever S in gamma, eventually S times Fn is almost the same as Fn. That's a minimal group. Now for the entropy, we take a finite open cover of X. We're going to look at, we're going to take more and more complicated covers, and sometimes we don't need the whole cover to cover X. So we're going to look at the minimal size of subcovers. So the minimal number of elements of U needed to cover X. And we're going to pull back various the open covers. So we'll get a bunch of open covers. We're going to take a join of them. So for two open covers, the join is simply just say A intersecting with B, where A is in U and B is in V. So in the picture, this is maybe this is U and the other one is V. So you put them together to get the final cover. Then the entropy for x under this finite open cover u is simply just taking the logarithm of n joining of u, but you pull back, it's under the elements in Fn, take the join of them, look at the minimal number you needed, then look at the growth rate of it. So take log divided by the size of Fn, then we take a limit. Then this will be actually a finite number. So this will be actually at most the size of u. And the once lemma guarantees that actually the limit exists, then it does not depend on the choice of Fn. Yeah. For this number depends on u. If you want to get rid of u, so that will get one number which only depends on the action. Then we'll simply take the supreme over u. That's the entropy for the whole action. Then this still non-negative number, but possibly one gets infinity. So that's the definition of entropy. Now, the study of the relation between these two actions was started by Bauer and Sigmund. So let me say, just say formidable gamma Bauer and Sigmund in 1975 systematically studied the relation between these two actions. Or let me mention that this is how it's defined, but dynamically the intuitive meaning for the entropy is the complexity of the action. So the bigger value you get, you should think that the action is more complicated. And here, of course, one can embed x very naturally into the property measure space. Each point, you just look at the point mass. Okay, yeah. So the complexity here is definitely higher than the complexity of x, at least the same as complexity of x. Okay. Yeah, in particular, if you go to entropy, it's not surprising that the entropy here should be bigger, or at least the entropy here. Okay. Yeah. But what Bauer and Sigmund showed is that if entropy of x is positive, then the entropy on the proper measure space is actually infinity. Yeah. So this is well, intuitively it just says that if here it's complicated enough, then when you go to proper measure space, it will blow up. It becomes much more complicated. But the proof is actually not difficult. It's very straightforward. They showed it only for Z, but it's easy to carry out the proof for a minimal group. Recently, people have obtained much stronger results than this one. So last year, Bergot and Lucy, and this year, Shi and Zhang, they showed that they improved this result to show that if the entropy on X is positive, then the mean dimension for the proper measure space is infinity. Yeah. Actually, they showed it for integer group, and then Zhang extended to a minimal group. Though the major idea is actually already in the integer group case. Okay. Yeah, I'm not going to talk about the mean dimension, though this is connected to operator algebras connected to classification program in some other way, related to the convergence of readers. Readers of comparison, we look at the cost product algebra. But let me just mention that this is dynamical analog of mean dimension, and even say the mean dimension is positive already implies that entropy is infinity. So this tells you that this is infinite, tells you that it's positive, then tells you that this is the entropy is infinity. So this is way much stronger than this statement. Still, these two results, the spirit of these two results, as I mentioned, says that if the complexity here on X is large enough, then when you go to M of X, it's way much more complicated. But what about the other direction? So if you think about this, the other direction is actually a little bit surprising. This was done by Glasser and Weiss in '95. And they showed that if the complexity on X side is very small, is very low, then the complexity on MX is also very low. So if MX has positive entropy, then X also has positive entropy. In other words, if the entropy is 0 here, the entropy here is also 0. Yes, all this is for minimal. Yeah. M of X, yes, it has, yes, correct, that's correct, yeah. The main reason is that it's convex, just. Zero if and only if and only if the entropy on X is 0. Yes. Yeah. And then they actually, Glasser and Weiss actually proved it only for Z, but with a little bit extra work, one can carry over the proof for minimal groups. Also for integer case, they actually gave 2 proofs. The first proof only works for Z. Second proof, if you do a little bit of work, you can make it go through to minimal groups. And the K in the second group actually uses function analysis. The K in the second proof is something related to Balance space. It talks about the maximal value for n for L2 space embeds into X, I should not use X here, into a Balance space way. Okay. And you want to put some control on the embedding because infinite dimensional Balance space embeds into it. If the dimension here is at least n. So you need to control the embedding. So you look at the norm and look at the inverse from the image back to the L2 space. You require that the product is controlled, okay. Yeah, by constant. Then you look at the maximal n there. The result needed here is that this maximal n, of course, depends on V, but so this is basically constant times logarithm for when V is actually infinity. But it's constant times m for V is L1 space. Yeah, that's the K Balance space result needed in this proof. So as Chris already observed that if you put all the results together, in fact, the picture is actually very, very clear already. The entropy here on X is 0, if only if the entropy on Mx is 0, and for Mx, the entropy is either 0 or infinity. Yeah, you can also even put mean dimension being positive and the mean dimension being infinity or into these equivalences. So it looks like everything is very clear. There's nothing more to talk about. But as we're going to talk about the local entropy theory, we'll say that, in fact, this is just the top of the iceberg. So in fact, there's much more below it. Okay, yeah. So let's get to the local entropy theory. So we're going to use delta x to denote the diagonals on X. The local entropy theory was started by Blanchard 30 years ago. The definition is the following. So if you take a pair of points in X but not on the diagonal, this is an entropy pair if for any closed neighborhoods AI of xi the entropy for this cover will be positive, where this open cover is simply just a complement of these AIs. So in other words, this is X, then X1, X2. You take tiny neighborhood A1, A2 closed of these points. Then you look at the complement of A1, complement of A2. That's an open cover for the whole X. Okay. Of course, if in fact the main thing is what happens when A1 and A2 are very, very tiny. Okay. Yeah. Then when A1, A2 gets smaller, this value here becomes smaller. But the one that is required is always to be positive. Yes. Yeah. But yeah, the main what we care about is whether just is positive or not. Okay. We don't really care about the limit when A2 gets very, very tiny. So this is how. Here is how this is related to whether the entropy is positive or not. Blanchard himself showed the entropy is positive if and only if there are these entropy pairs. Blanchard introduced this notion just main reason is to find the topological analog of something happens in multiple reactions, so-called complete positive entropy actions. Yeah, but when you look back, you can think that this is kind of a localization of entropy to tell you where positive entropy comes from by pinning down to points instead of just the whole action. So it's basically saying that the positive entropy just comes, the entropy being positive comes from this pair of points. But it's still a little bit unusual because usually when you do localization, you go to just a point. But here the localization is going to actually a pair of points. It's not just a single point. This solution, though, again, the proof between the equipments here is actually a lot very complicated because somehow both sides, even this side, when you look at the definition, it already involves entropy directly. Okay. Yeah. But still, this solution is fairly useful, especially people have developed measure version for the solution. And one can use variation principle, things like that, to go down to the measures, then carry out various things. People have used it to prove, for example, if the entropy is positive, then it's so-called Lyot chaotic. Yeah. Now we're going to give another description of the entropy pairs using so-called combinatorial independence. So here is basically introduced with David many years ago. So now for in general A1, A2, a pair of subsets of X, we say one subset of the group is an independence set for this pair if for any I inside of J, which is non-empty and finite, any function on I2, 1, 2, this intersection S inverse A sigma S in I, this is non-empty. Yeah, but what are we talking about here is the following. So you look at so this is X, this is A1, A2. The interesting case is that actually they are disjoint, but in the definition we don't require that. So you look at the case, just say J is simply just I, you get like 3 points, G1, G2, G3. Okay. Then what you do is you look at the copies of A1, A2. And G1, G2, G3. So the requirement here is that if you want 1 point, under the action of G1 goes to one of these 2 sets, A1 or A2. So under G1, you want it to go to A1. Under G2, you want it to go to A2. Under G3, you want it to go to A1 or A2. You make a choice. You can always find 1 point doing that. That's what the condition is talking about. Then we say this pair of subsets as positive independence density if there is this part of constant say, which is supposed to be basically just density, such that for any f in gamma non-empty finite, there is this j in f with the size of j is at least the size of f. So that means j has density at least c inside of f. So that this is actually an independent set. For this pair. Then we can say one pair of points, x1, x2 in x squared. This is an IE pair. So this means positive for independence density pairs. If for any neighborhood of x, any neighborhood AI of xi, you look at the pair of subsets A1 and A2. It has positive independence density. Yes, yeah. So, yeah, the density here, say, depends on A1 to, when they become smaller, say, becomes smaller. So, yes, yeah. So the definition here does not involve entropy anymore, and the relation with the entropy pairs is the following. So Huang and Ye showed first for the case the group is just an integer group. They showed that the entropy pairs are exactly the same as non-diagonal IE pairs. Okay, that's what they showed. So these two things are basically, these two definitions are really equivalent, just that here you allow x on x to be equal, here you don't allow that, but once you require them to be not equal, then they are really the same. Yeah. The proof uses invariant measure. You have to go to invariant measures doing algorithmic theory there. But then with David, we showed that for a minimal, more general, a minimal case, actually, this is true. They are really equivalent. But then the proof uses just the combinatorics. No invariant measure is needed. What is x? X is still just any the measurable space, any minimal group gamma acting on it continuously. Yeah. Now, if you put this with Blanchard's result together, if you not worry about the history, then the summary is for a minimal gamma, the entropy is positive. The same as in that there exists non-diagonal pairs. But then we can, oops, should use the other board. Okay. then we can rephrase the cluster Weiss result. Now this means that if we look at, now let's give a notation, say IE2 of X just means all the IE pairs. And let's just say that the IE pairs of X, if we look at the non-diagonal thing, this is non-empty, if and only if we go to M of X, the IE pairs, non-diagonal IE pairs, is non-empty. So cluster, I mean, this just says that entropy on X is positive. This says that entropy on Mx is positive. Yeah. But then once you phrase the result in this way, then you see that the true question one should really ask is actually the relation between these two sets. So the real question one should ask is, say for example, you can ask it in inverse ways. So can we determine the IE pairs for f of X using the IE pairs of X, for example. Okay. If we can we explicitly write down this part from the information about this one? Yeah. Yes, that's easy. Yeah. So you can say this is contained in this one. Okay. Yeah. So, but still, if you load the image, so you know part of the points here, but still, how can you describe the whole set? Yeah. So now, let me. Now we can write down the first result. For mutable gamma, here for entropy theory, we're talking about mutable gamma. First thing to notice is that this part is actually fairly straightforward when you use the correct definition. The IE pairs on M of X, you notice that this is actually containing M of X square by definition, but M of X is actually convex. So it's very natural to ask whether this is actually convex or not. The answer is that actually this is convex. From the definition, it's also easy to see that the IE pair, this set is actually always closed. And the gamma invariant. Okay. Yeah. So for function analysis, people, once you see close the convex, it's natural to ask the next question. Okay. It's the closed convex of which set? Okay. Yeah. And here is the answer. Because it's can already notice that IEX is actually contained in here, so that's a natural candidate. Yeah, so this is actually the closed convex of IE pair of X. So this already answers that question. This is how you can determine the IE pairs on M of X from the IE pairs of X. Right. And this already gives us the result of Glass and Weiss, because this is taking the closed convex Hall. So if this part, if this is everything here is in the diagonal, the closed convex Hall would still be in the diagonal. he used to get infinite. To see that on m of x, once you get partial entropy, then it's infinite. That's already fairly easy. You don't really need this. Just from the I pair definition. From this definition, you can already get that. Yeah. Well, not from definition. You have to do a little bit of work, but it's fairly easy. And one can actually also, in this way, you actually, to describe the I pairs on M of X, you need two steps here. You take the convex combination, then you take a closure. Okay. So for function analysis, people will say, okay, take a closed convex, so it looks like just one step. In fact, there are two steps involved. One can describe it in another way so that you only involve just like taking basically just one step. So you look at property measures on x squared, you put mu I, just the projection, the push forward of mu onto each coordinate. Yeah. So for here, pi I is simply just the coordinate projection from x squared to x. Yeah. Then, in fact, the I pairs on M of x is simply just you take mu as property measure, but not on the whole x squared, but on just the I pairs. Okay, because this this part is actually containing x squared, so close a subset there. You take all those property measures, then push down to I think what I'm seeing. Yeah, push down them to x. So this is one element in mx. This is another element in mx. So it's a pair of points in mx. Then that gives you all the I pairs on mx. Oh. So now maybe I will just give the consequences. The first is that you get the cluster-wise result. Okay, so now the proof is purely just combinatorial. Well, here is the only function analysis involved is just the Hamilton theorem. So that's the only thing in function analysis is used in the proof. Okay. So another thing is cluster-wise result is concerned with the case the I pairs is as small as possible. Okay, basically all contained in diagonals a lot. Okay. The other extreme is when it's actually very large. This is actually the so-called the UP case. Then people have studied these cases. So the people showed that IE pairs for x is the whole thing, everything possible, the whole x squared, if and only if for m of x, the same thing happens. Okay, so these people did it for these people did it for more generally a minimal group, though they actually did also more on extensions. Okay. Yeah. So another thing is if you put natural number n, if we put mn of x, just all those probability measures, but we require them to be the support of mu to has at the most n points. Okay, just convex combination of delta measures. Then what happens is that if I have n1 x times n2x being an I pair. So in other words, we're looking at I pairs on M of x, but each of them, each coordinate, actually has finite support. Okay. Then in the definition here, you see that when you find this one is probability measure, but of course you can change it slightly to make it have finite support. Okay. But as the sets become smaller and smaller, maybe the support of this point here actually you need a lot of points there. In general, that's what you can imagine. That's what we're seeing here is that once you know that the 2 points have just finite support, then actually here you can just require a uniform bound on how many points you have for this one, for the support. So this is actually already one I pair when you just look at the probability measures with support at the most n1 times n2 many points. So that's everything about the entropy case. Next, I want to mention another one. So I will mention just the so-called tameness. This dynamical property has origin in function analysis. Started with Rosenthal's result. He gave a calculation of balanced spaces containing copies of L1 space. Yeah, but then this dynamical property originally is called the tameness. Originally was defined as just as one dynamical analog of it. Now gamma acting on x. So now this time we don't require, no need to require it to be a minimal anymore, just any countable infinite group. We say this is untame if the continuous functions on x contains a copy of L1 dynamically. Okay. What it means is that there is a set J in gamma infinite, and one continuous function on x, such that when you look at the map from L1 of J to C of x, you simply send this lambda s to you treat them as use them as the coefficients. Take a convex combination, linear combination of the images of S of F under S. Yeah, this is an isomorphism. To its image. That's the requirement. So this is defined originally using analog of Rosenthal's result, but later people have found various dynamical calculations of it. For example, you can characterize it using the so-called Ennis semigroup of the action. Then one can also modify the definition here of the IE pair to characterize the tameness, then we'll see that this is one IT pair, means independence on tame pair. If for any neighborhood A1, A2, what happens is that this pair of sets here has an infinite independence set. That's the change. Earlier we required the partitive density independence set. Here just simply require just one infinite independence set. Yeah. Yes. Yes. So IE pairs will automatically be IT pairs. That's true. Yeah.
You can extend this statement to
Huh?
like the original definition just said for every finite f, there's
Yes. If you find f, it does not tell you one infinite set being like having partitive density in some sense. Yeah, but you can prove that. Yeah. Then with David, we showed that actually this characterizes whether the system is on tame or not, just like in the partitive entropy case. So it's on tame if and only if there exists non-diagonal IT pairs. Then, so you can see so far that things work basically parallelly. Okay, whatever you have in for IE, now you have it similar for IT. So you can ask what happens here. Okay. Yeah. When you go to for the main theorem, so whether everything is still is true when you everywhere you replace IE by IT basically. Yeah. Of course, now we're not looking at minimal group just for any counterpart infinite group. But apparently somehow this is not true even for the first statement. This actually is not convex in general. But once this is not convex, then it looks like it breaks down, then you cannot even expect what to talk about here. But this part is still true. It's contained in the closed convex hull. That's still true. But this does not determine this set yet because it's only a subset of it. Okay. Yeah, you don't know which points are really in here. Okay. Yeah. But one can still. It turns out that this set is still determined by basically what happens here, but not just you need a little bit more. You need not only just the ID pairs on X, but also you need ID pairs on X to the N for all N. So what you need is the following. So for each N, you put Bn to be the convex combination of say delta X j delta Yj for all So you get two pairs of many pairs of points on X. You take the convex combination of the point mice. But for these pairs, what you require is the following. So x1, x2 until xn, y1 until yn. This is one active pair in x to the n. So you need not only the active pairs on X, but also active pairs on X to the n for all n. Okay. Then this one here, active pairs of f of X, is simply just you take the union of these pairs and take the closure. So that this is still determined by not only just the active pairs on X, but the active pairs on all X. Okay. Yeah. I'll stop here. Yeah, thank you.